Okay, so what is polynomial representation? Well, sometimes what happens is you are presented with data of a certain physical quantity. Let's say you know something about the temperature at different times in the day. So at 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, and you need to find the rate of change of temperature at 1.5 or 1 hour 30 minutes. So it's like you need to find the derivative at a point in between the times in which measurements are made. And then the question is, how do you do that? Well, polynomials is one way to do it. So let me re-explain what I said by a simple plot. Okay, so there is a physical, there's an independent variable x, and there's a physical quantity f of x. All you have with you is data at some points. Okay, and you're told to compute the derivative at, let me just move this a little bit, say here, here, and here, and perhaps here. And so what you're told, you're given the values of f at those 5 points I drew there, and you're told to compute the derivative at, I don't know, let's maybe say over here. Compute f prime x. Okay, so that seems quite hard because first of all, you don't have data at that point. And if you don't have data, how will you even go about computing the derivative? So one trick is to fit a curve between all these points and then use that curve to compute the derivative. So in this case, if there are 5 points, and if you wanted the simplest possible polynomial, then it would be a 4th order curve, right? So you will fit a curve a0 plus a1x plus a2x square plus a3x cube plus a4x4. Just write it again here, down maybe. a0 plus a1x plus a2x square plus a3x cube plus a4x4. Okay, so the question is why 4th order polynomial? Well, you're given 5 points. So we can evaluate 5 constants, and 5 constants appear in a 4th order equation. So 4th order will give 5 constants. And so the claim is that you can then find those 5 constants using the values at those 5 points. So once you do this, this is step 1. Step 2 would be you can then take the derivative of f. So it'll be a1 plus 2a2x plus 3a3x squared plus 4a4x cube. And now once you have the derivative, you can sub in the value for whatever that point is, some x star, and if you put x star, you'll get the value. So that's the motivation behind using a polynomial representation. It just depends on the number of points. Now, polynomial, is it the only way to do it? That's not right. You can use any polynomial. You could use, I don't know, sines, cosines. You could use exponentials. Sometimes you know something about the phenomenon. It is maybe there is an exponential growth somewhere, so you do an exponential. But by far, using a polynomial is perhaps the most simplest way to do it.
So if there's more points, you use a higher order.
Right, you use a higher order, right? It turns out that if you want to go more in details, if you have like 20 points, then you probably don't want to use 20 or 19th order polynomial. That's because what happens is with that high order is that once one point moves a little bit, all the constants will change in that polynomial, because that polynomial is based, that the curve fit is based on all the 20 points. What they typically do is they'll usually fit a spline between 2 points. So it'll be a third order polynomial between 2 points, any 2 points. And that way, even if you change, let's say, the 20th point or 19th point, then all the 17 curves for the 17 point, the 17 splines will not change, because they only depend on the local information, but will not get there. You typically want to restrict yourself to low order polynomials, but for this part, don't worry too much about it. So what we'll do is we'll do an example involving we'll do an example where we have 3 points. So just to show you how this works, so let's say that if we are given 3 points, then obviously you can fit the simplest curve is going to be a second order profile. So this will be second order. So let's just go through the math and see how it comes out. So what we have here is we're given the value f1, f2, f3, and these points are, let's say, x1, x2, and x3. So we know x1, f of x1, that's the first point. The second point we know about is x2, f of x2. Third one is x3, f of x3. So given this information, we can assume that f of x will be a quadratic equation where a's are unknowns. So we assume this equation. Once we have this equation, what we'll do is we'll sub in the value of x and f of x. So let's do substitute. Equations. So that would give us 3 equations. So first one, just put x equals x1. So we have a0 plus a1 x1 plus a2 x squared. F of x2 is a0 plus a2 x2 plus 3x x1 square x2 square. Wait, I did something wrong. A0 a1. Sorry, this should be a1 a2. F of x3 will be a0 plus a1 x3 plus a2 x3 square. Okay, so remember that you'll actually be given values for x's. Now, one way of writing this, if you want to do it an analytical formula, is you can write this as f of x1, f of x2, f of x3, and then this would be 1 x1 x1 square, 1 x2 square, 1 x3 square, and when I multiply it with a0 a1 a2. So you can check that if you multiply that matrix of 1x x1 square and so on with a0, you'll actually end up getting the right hand side. Okay. So if you write this as, and let's call it f, let's call this capital X, and let's call this a, the unknowns. Then if you want to compute the constants a, all you'll do is either x inverse f. Remember, this is 3 cross 1, 3 cross 1, 3 cross 3, 3 cross 3, 3 cross 1. So 3 cross, just move it down. So a is x inverse f, 3 cross 1, 3 cross 3, 3 cross 1. Okay, now this is actually frowned upon, the x inverse. If you write it as, if you do inverse x times f, it's a valid operation in Octave or MATLAB, but MATLAB will always complain saying that don't use inverse x, instead use x slash f. This basically is same as inverse x. Why do you want to do it? It uses better numerical calculations to figure out the inverse as compared to this one. It's numerically more stable, this operation x backslash than using inverse x. So MATLAB, for example, will specifically complain about using inverse. But if okay, so once we have computed x, what does x mean? It basically, well, what does this a mean? What does this a mean? It basically gives you the constants, the three constants. Once you have that, you have completely determined what f is. So the last step, third step is, sorry, the second step is to actually get f of x, which is a0 plus a1x plus a2x squared. Now we know what these constants are because they came from here. The third step and the final step is to compute f prime, which is the derivative of a0 is, well, 0 because it's a constant. Then we have a1 plus 2a2x. Then you can sub in whatever value you want to x, and you have f prime x. Okay, so let's do this, an actual problem, and see what we get. Okay, so this would be our problem 3. The values of f of x at x equals 0, 1, 2 are equals 2, minus 1, minus 2, respectively. Compute f prime at x equals 0.5. You could also write this as f prime at 0.5. Okay, the same thing. Okay, the first thing we notice is that there are 3 points. Right, so 0, 1, 2, whose values are given. So we assume f of x to be a0 plus a1x plus a2x squared. So first step is we will compute the constants a0, a1, and a2. For that, what we do is we sub in the values f of x at 0 is 2. So I put a0 plus a1 0 plus a2 0 square. So this gives me 2 equals a0. So the nice thing here is that just because there's a special point 0, it actually gives me one constant. I don't really have to do the inverse of a 3 by 3 matrix. So let's use the second point. So x equals 1. So the value at x equals 1 is minus 1. So at x equals 1 is minus 1, but I need to sub that in this expression. So a0 plus a1 1 plus a2 1 square. Okay, now I'm going to use the fact that I know what a0 is. It's 2 plus a1 plus a2. Okay, so effectively I have a2 plus a1 is minus 3. Okay, last I'll use the third expression. I know that at x equals 2, the value is -2. So let's use that. -2 equals a0 plus a1, sorry, 2 plus a2 to square. So a0 is known, it's basically 2 plus 2a1 plus 4a2. You can actually, let me simplify this. 4a2 plus 2a1 equals -4. I can do a little bit more simplification by dividing the both sides by 2. So I'll get 2a2 plus a1 equals -2. We call this 1, let me call this 2. I would need to solve for a1 and a2 from those two expressions. Okay, so let's do it on the new page. So I'm going to rewrite those expressions. So one of them was a1 plus a2 equals -3, and a1 plus 2a2 equals -2. I think what I did was I just switched the order just so that it is, I wrote a1 first, a2 after that, and that's why it's just a little bit easier. So a1 plus 2a2 equals -a2. Okay, now we have, well, one way to do this is to use that x slash so on, right? You could write this as a matrix. So method 1, if you have access to a calculator, if you have access to a computer or Octave, you could just do it this way. And then you need to compute the inverse. And then multiply the two. Okay, so I don't have access to a calculator right now, but you could, if you have a calculator which can compute the inverse, you can do it. You could also do that by hand, of course. But here's another way to do it, which is probably the method you would use if you do not have a calculator. You could just subtract one from the other. So if you have, I think I wrote this as 1, this as 2. So if you do 1 minus 2, you basically eliminate a1, right? So if you do this minus the one below, you have minus a2 equals -1. So a2 equals 1. And then once you have a2, you can just sub it in any of those expressions. Sub a2 equals 1 in, let's say, 1. a1 plus a2 equals -3. a1 equals -4. So we've got a1, we got a2, and a0 was already 2. Okay, so let's start with an expression for f of x. a0 plus a1x plus a2x squared. I've completely found the constants. a0 is 2, a1 is 1, sorry, a1 is -4, a2 is 1. Okay, the last step is to compute the derivative, which is kind of easy to do now. 2 minus, sorry, derivative of 2 is 0. Minus 4x is 4 plus 2x. Specifically, if I want to find the derivative at x equals 0.5, I have minus 4 plus 2 times 0.5, which is minus 3. So f of f prime at 0.5 is minus 3. Okay, we've pretty much done with what we had to do in this course. The only last note I would add is for partial derivatives. If you're doing fluid mechanics especially, you will see partial derivatives coming quite a bit. Okay, so most of the things we've talked about, actually almost everything we've talked about with respect to differentiation is the complete derivative. We had, let's say, f of x, and then we computed df dx. This is the complete derivative. Now, partial derivative is when you have more than one variable, independent variable. So here x and y. And if you want to compute the value of df dx, what you need to do is you need to treat y as a constant. Okay, think of y as a numeric value. Don't do anything to y. That would be a partial derivative. Similarly, you can compute df dy, treat x equals constant. So an example, if you've, just to recollect, if you had f of x comma y equals xy plus x square minus 2y, okay, just made up example. If you are told to compute df dx, okay, so you need to differentiate this expression, treating y as a constant and doing all the operations you normally do for x. So in this case, xy, the derivative of, if y was a constant, derivative of xy would be y. So if derivative of 2x squared would be 2x, and then what would be the last term be? 0, right? Because y is a constant. Similarly, if you are told to compute df dy, you would take the first expression, keep x as a constant. So derivative of xy would be y, because, sorry, x, because y is a variable, x is a constant, plus 0, because, you know, x is a constant after all, minus 2. Okay, so that's how you would do a partial derivative. Now, when it comes to this course, what you'll see is that it's the same thing where you're given an expression, you're told to find the derivative. The formulas we derived for the forward difference, backward difference, and so on are simply applicable to this scenario. All you got to do is keep the other variable constant. So there's not much to be done here, except to then is to just write the formulas down. So what we'll do is we'll use a notation, and we'll not go beyond. I don't think we're going beyond 2 variables here, x and y. So what I'll do is we are normally interested in the derivative, the numerical derivative, and so we typically are given a point, and a point like say 0.51. So let's just call that f of xi yj. So that's 1 point. Okay, it could have x and y could have some values, but it's just some random point. and you're normally told to compute the derivative at that point. So just to make it easy to write these expressions and not write x, y all the time, I'll denote this as Fij. Okay, so it means that x, it takes xi, the value of x at xi, and y at yj. Okay, with that, we can now write different formulas down. So forward difference. So forward difference, as I said, there are two forward differences. One would be for f with respect to x and f with respect to y. So if you were to compute df dx, so the partial derivative at ij, what you would do is, remember that the x index is the ith index is associated with x. So you will do the corresponding substitution. So you will do, and I'll put down what this means. F of I plus 1j minus Fij divided by delta x. Okay, so what is Fi plus 1? Xi plus delta x yj would constitute Fi plus 1j. So it's the perturbation in the value of x. Similarly, we have f xi yj plus delta y as f of xi xi y j plus delta y f of I j plus 1. So you perturb the value of y and perturb the value of x. So forward difference is that for x, you can write the forward difference for y j plus 1 minus Fij, and remember it's perturbation in y. Okay, forward difference. We can do the same thing for backward difference. Okay, remember that backward difference is you go backwards in time or the independent variable x. So here we would have Fij minus Fi minus 1j divided by delta x, where I minus 1 would be x minus delta x. Delta y okay, we can also do a central difference. Running out of space, so I'll take a new page. So central difference looks a little bit forward, a little bit backwards. So let's do central difference. So I plus 1 j minus Fi minus 1 j divided by, this one is 2 delta x. Then we have df dy I comma j is I j plus 1 minus j minus 1 2 delta y. And then I'll put another one, the last one, this is the second derivative. Second derivative central difference. D square f dx square j would be f of I plus 1 comma j minus 2 fi comma j plus f of I minus 1j divided by delta x square. Then d square f dy square I comma j would be ij plus 1 minus 2 yj plus f I j minus 1 delta y square. Yeah, I hope you get the pattern. It's not very hard if you write these once you know how the central difference works for the complete derivative.